Now let's look at relational and non-relational databases. On the left side, we have relational or SQL databases. These databases store data in a highly structured tabular format, using rows and columns. Examples include MySQL, one of the most popular open source relational databases, PostgreSQL, known for its powerful features and compliance with SQL standards, Oracle, used extensively in large-scale enterprise environments, and Microsoft SQL Server, often used in businesses alongside Microsoft software suites. These are also commonly referred to as relational database engines, since they provide the core software responsible for storing, managing, and querying data. And while they all follow the same relational model, there can be some variations in SQL syntax and features across these implementations. Then we also have Amazon RDS, an AWS managed service that supports several relational database engines. And BigQuery, Google's fully managed data warehouse that uses SQL-like queries. On the right side, we have non-relational or NoSQL databases, which are designed for flexibility and scalability. They usually manage data that doesn't necessarily fit well into tables, such as semi-structured or unstructured data. Examples include MongoDB, a popular document-oriented database that stores data in JSON-like documents. Cassandra, used for handling large amounts of data across distributed servers. Redis, an in-memory key value store used for caching and real-time analytics. Amazon DynamoDB, a fully managed service by AWS with fast performance and scalability. And Cloud Bigtable, Google's NoSQL database designed for large analytical and operational workloads. This categorization highlights the different needs they serve: structured relational data versus flexible, scalable, and often schema-less data management. Okay, so let's talk about relational databases. First, let's look at the visual at the bottom left. This table with rows and columns represents how data is structured in a relational database. In a relational database, we store information in tables that are organized with columns defining data attributes and rows representing individual records. This structured approach ensures that data is highly consistent and easy to access through queries. Relational databases are highly structured and standardized, relying on predefined schemas that determine the layout of each table and the types of data they store. They contain rows and columns, with the columns defined by the schema. This consistency is key to maintaining data integrity and consistency, ideal for applications where accuracy and relationships between data are crucial. On the right side, you can see examples of relational databases supported by Google Cloud, like Cloud SQL, AlloyDB, Spanner, and BigQuery. These services help manage data in a relational, highly organized manner that provides robust data analysis and operational reliability. Now, let's look at how GCP handles compatibility for most common database engines. Let's start with PostgreSQL. If your application relies on this engine, GCP offers three primary paths. Cloud SQL for PostgreSQL provides a fully managed version of the standard engine. AlloyDB is a PostgreSQL-compatible service designed for demanding enterprise workloads that require higher performance. Spanner also offers a PostgreSQL interface to give you the benefits of a horizontally scalable, globally distributed database while using familiar tools. For those running MySQL, GCP provides a dedicated version of Cloud SQL for MySQL. This allows you to migrate your existing MySQL databases into a managed environment without changing your underlying code. If you are currently using SQL Server, you can reach for Cloud SQL for SQL Server. This service manages the infrastructure and maintenance while providing the specific engine features your applications expect. Each of these Cloud SQL versions runs its respective database engine. This means that for PostgreSQL, MySQL, and SQL Server, Cloud SQL is executing the actual engine software. In the case of AlloyDB and Spanner, the system is compatible with PostgreSQL syntax and tools. While they may use different underlying architectures to achieve better scale or performance, they speak the same language as PostgreSQL, maintaining SQL compatibility. So, for example, if an exam scenario involves choosing a database to run a MySQL or SQL Server workload, Cloud SQL would be the correct option, as it is the direct path for migrations where engine consistency is the priority. Now, while the options we covered focus on supported database engines, some migrations involve conversions from unsupported database engines. For example, you might choose to migrate from SQL Server to AlloyDB for PostgreSQL or move an Oracle database into Cloud SQL for PostgreSQL. These paths require more effort during the migration phase, but allow you to move to supported database engines. Now let's switch to non-relational databases. Let's start by taking a look at some visuals to get an understanding of the different types of data models used in non-relational databases. On the right, we have an example of a data model that would not neatly fit into a fixed schema. It's called a graph network. This type of model is excellent for representing complex relationships between entities. Imagine a social network where nodes represent users and edges represent connections between them. In a graph database, these kinds of connections can be stored and queried efficiently. This type of structure does not fit neatly into tables or rows, as it is inherently about relationships rather than a fixed number of columns. And below, we have a key value store example. Here, data is represented as a collection of key value pairs. For example, the key user ID 1234 maps to a value that contains user details like name, age, and location. And then another key, user ID 5678, maps to a completely different value. So notice how the data under each key is different in structure. Some keys have detailed personal information and others only have user preferences. In a relational database, this kind of inconsistency would be difficult to handle, as every record needs to adhere to the same fixed schema. Key value stores are used precisely because they provide flexibility when different records need different types of information. This is actually also an example of a document store model. It's similar to key value, but allows more complex nested structures, which are great for handling data represented in formats like JSON. The value in this case is a structured document containing nested fields like preferences. The document store type of models allows you to store entire documents, and each of which can have different fields, providing even more flexibility. These examples help illustrate why non-relational databases are so powerful. They are designed to handle unstructured or semi-structured data that doesn't fit into the rows and columns of a relational table. Non-relational databases provide flexibility for situations where data models might evolve or vary significantly. So, to summarize, non-relational databases are ideal for storing and managing large volumes of data that do not fit into a typical tabular format. they can more easily handle a variety of data formats, whether it's semi-structured or unstructured data. The data model flexibility includes document stores for complex nested structures as shown below, key value stores for diverse types of data associated with a unique key, again as shown below, and which document store is a subset of, column family models for wide column databases, and graph models as seen in the visual, which map out relationships effectively. This kind of flexibility allows non-relational databases to excel in use cases where schema-less storage and scalability are key. Non-relational databases allow you to scale effortlessly by eliminating the need to redefine the entire schema whenever data evolves, making it easy to accommodate growth and changes in your data structure. On this slide, we are comparing relational and non-relational databases in terms of their pros and cons. Let's start with relational databases. The pros include standardization. Relational databases use a standardized query language, SQL, which is widely adopted and understood. They are the go-to choice for analytics and data science tasks that need structured data and complex querying. And ACID compliance is another strength, ensuring consistency and reliability for transactions. However, relational databases come with some cons. They can face scalability challenge when data size grows significantly. They struggle with semi-structured or unstructured data, which doesn't fit neatly into tables. And there is also the schema rigidity. Making changes to the data structure can be cumbersome. Moving to non-relational NoSQL databases, the pros include excellent scalability, particularly for distributed systems that need to scale out horizontally. Flexibility in data models allows you to store various types of data without rigid schemas. They are well suited for big data applications, allowing for more efficient handling of very large datasets, and higher performance is often achieved, especially for reads and writes at scale. On the cons side, lack of standardization means that there isn't a single query language like SQL, which can make querying less straightforward. Non-relational databases are often less ACID compliant, which means you might trade off consistency for scalability. And analytics and reporting can sometimes be more challenging because of the lack of a rigid structure, which makes aggregations more complex. So each type has its strengths and weaknesses, and the right choice will depend on the use case, whether you need the rigidity and transactional consistency of a relational databases or the flexibility and scalability of NoSQL databases. And that's it for this lesson.